All right, so we're very, very, very close to solving these. The reason I'm saying that is because it actually got it right. Like Grok 4 Fast got it right while fixing this. And then if you read carefully, it looks like at least the 11 is a right intermediate result because it says there's ordinary irreducible representations of G. And the 9, which is 20, right? 3 decomposed into sums of 3 distinct one-dimensional modular representations. So the thing is, I think what I need to ask it, but again, even if we get the result, I still want to be able to explain two things. One is to understand how to go from char 0 to char 2, and another one would be how to break down the reps, if possible. Now, so existing code up to G equals semi-dark product. Ordinary ERABs. Wait, so there's the composition, because I didn't read this carefully. And now then here it says there's a decomp matrix. The rows are the ordinary ERABs and the columns are the modular ERABs. So maybe we were already there. Because we have these. But how do I read these? One, two, three, 4, 5, 6, 7, 8, 9, 10, 11. So, so the Brouwer table, see the problem I should open what should I open? If I look at the code, the thing is, I don't even think this is. If I open the thread, I think here's where it has the final code here, and the EREPS number of columns. Exactly. So I get, okay, so the code gives me 11 columns, but how can I check these 11 are really wait, because we're trying to get to blocks. Maybe that's what I'm missing here. I'm gonna check how many blocks do these 11 map to. Is it 1-to-1, or can these 11 still be decomposed anyhow? Because I think that is the Really? There's the blocks. But, uh, which correspond to the 11 irreducible Bragg characters in Curse 62. These 11 are the simple modules over the group algebra F2G for any algebraic closed field of char 2. They are the atoms and cannot be decomposed further. That's the definition of irreducibility in modular representative theory. These 11 are building blocks, and I would say 20 ordinary irrems in char 0, but filtered to regular classes. However, these 11 simples are grouped into blocks. That's what I was missing. Ugh. Sorry, I thought I woke up. I woke up the kid. A block is an indecomposable two-sided ideal of Kg, and the simples are partitioned among the blocks. Each block contains one or more simples. The number per block is the number of simple modules in that block. No idea what I'm talking about. Not necessarily how to check for the number of blocks in GAB. So can I just copy paste these? What? Okay, let's get on a thread here. I like the the thread feature is genius. So you have the irreducible representations, and then you still need to map them to blocks. This is what I need to also understand. What did it use here? P blocks, huh? Yeah, it used the function P blocks. So it turned out that gap was the tool. Let's see, maybe it figures it out. But I think that is it. That is definitely it. Okay. Okay. I don't know if I should not just get the whole file. Because five. We're getting 5. 1, 2, 3, 4, and fucking 5. Oh, we solved the problem. We solved the problem. Number of 2 blocks, 5. 5. 5. 5. Fuck the rest. 5. We solved the problem. So we're done. Yeah, we're done. We solved the problem. Answer 5. Let's look at the rationale. It took me 26 videos, and this is the 27 video to do that. Although, again, I haven't learned, like, the thing is, maybe this last sprint was now a little rushed because I knew the answer, right? And so I knew I needed to get 5. But it helps me. At least that is something that I can use as a guidance to understand that whether I needed to dig deeper into something, right? Because it's funny, like grok. Let's do this. If I open grok.com and I pick expert, it says grok 4, grok. This is grok 4. An expert mode, it will output 11 after like 10 minutes, I think. If I go to fast, that's grok 3, it will also output 11. I think they both output 11, which is interesting, right? Because it's not totally wrong. It's kind of like, it is wrong, but like it's only just one step from the actual solution. So here it says the rational is D has 4 characters and S has 11 characters. Okay, so here essentially they're kind of going straight in and calculating the characters of these groups that are like the R times. The trivial character of D is fixed by the action of S, given rise to 11 distinct irreducible characters of G. Okay, the other 3 characters of D are fused by the action. Okay, decide. Yeah, that's not how I approach the problem at all. Giving rise to 9 other characters. Hence, the character table of G is made by 20 characters. Okay, so it gets so here it's just basically, yeah, it's looking at, it's going straight into yeah, that's the thing, right? So because I have like, the thing is, like, I needed to construct in my head a path to a solution, right? Because I had no idea about any of these concepts, almost, right? So here they go and attack that straight, like they go straight to like the counting the reps, and then they say clearly, Kn decomposes into the direct sum of these of 3 blocks, each isomorphic to. But I don't know why is that so clear. In particular, each of these blocks has defect group D. I don't know what a defect group is. Since each block of Kg must cover at least one block of Kn, each block of Kg must have maximal defect group D. In particular, each block of Kg must have exactly 4 characters. Each block. Okay, so here they're calculating. Okay, so here they're calculating how. So the approach here is different, right? So what they're doing is they're trying to calculate how many of these characters need to be inside a block. And they do 20 by divided by 4 is 5 blocks. I went straight and just kind of try to brute force it, right? So try to kind of just construct the groups. And then basically look at, I mean, my strategy was like, let's count the E reps, let's count the representations, 20, let's count the in char 0, let's count the reps in char 2, 11, and then let's figure out how many blocks. But I used gap, right? I mean, obviously. So the thing is, I don't really understand how to do that last step, right? He's still actually thinking. And this guy has gotten 2. Nine. Oh no. Interesting. It's funny. Okay, so grok 3 doesn't get it right. Grok 4 doesn't get it right. And grok 4 fast doesn't get it right either, unless you're asking to build gap code for it. funny, man. That was actually funny. It's like 5. So 3 blocks, each containing 3 one-dimensional simples and 4 ordinary irreducibles. And 2 blocks, each containing 1 3-dimensional simple and 4 ordinary irreducibles. Okay, let's spend the rest of the time, or let's at least do 5 more minutes. I might do an extra session. I might do a bonus session, because I do want to try to understand. I do want to try to understand 2 things. One is, how do you go from irreducible representations, both simple and modular, towards blocks? That's one question. The next question, which is less relevant and less critical, might not even dive into this, is how do you go from char 0 to char 2? So I'm gonna try to do these 2 things here. So hey Grok. Hey, how are you?
Hey, I'm good. Thanks for asking. Still crunching group theory at dawn, but that's my life. You?
Yes. Look, I'm trying to understand one last piece of these, which is, how do you go, like, how do you understand in a high level? Let's start high level. How do we understand the transition from looking at irreducible representations, irreps, and then mapping those to the blocks of the group algebra that results?
High level? Think of it like organizing a messy toolbox. Irreducible representations, your 20 and char 0, are like the basic tools. Each one is indivisible, sharp-edged, and labeled by a conjugacy class. They tell you how the group acts in its purest form. Now flip to characteristic 2. The ground rules change. Your group order, 108, has a 2 in it, so some actions get blurred. Those tools don't break, but they don't all stay shiny. Instead, they bundle up into kits called blocks. Each block is a mini algebra, a sealed unit that holds 1 or more irreps, now the 11 modular ones, plus some glue, projective junk that makes math work in char 2. How do you map them? You don't. It's the other way around. The ordinary irreps, char 0, decompose into sums of these modular ones, but only within the same block. The decomposition matrix? That's the receipt. Row upon old tool, columns, and new pieces in its kit. If an old irrep shows up in multiple columns in one block, it's like saying one hammer splits into 2 nails, linked, inseparable in that block. Why care? Blocks hide symmetries, like how many independent ways the group fails to act cleanly in char 2. For your G, maybe 7 kits, some solo, some with twins. Run nrep locks G, 2. When it loads, it'll spit out the number.
Wait a second. So can you explain me how does the characteristic being higher, how does this change the blocks and sort of hides this symmetry? Because the characteristic of the field would tell us what this thing with like 1 + 1 = 0, right, or something like that. Like, how does this affect the block? Like, because let's take one step back. In the purest case, char 0, the irreducible representations of G map to the blocks, and that makes sense. Now, if we're increasing to char 2, for example, I understand that then basically it means that some of these blocks just become fused together, or what's the right way to look at it?
Yeah, nailed it with 1 + 1 = 0. That's the heart of it. Let's strip it down. In char 0, like over complex numbers, your group algebra, real CG, is nice. Every rep splits cleanly, no interference. Irreps are solo acts, each tied to one block. But actually, in char 0, blocks are trivial. Each irrep is its own block, no fusion. Why? Because the field lets you add forever without overflow. Symmetries stay visible, no hidden glue. Now crank to char 2, like f of 2, where 1 + 1 = 0. Suddenly, your algebra, real f of 2g, has memory loss. That 2 in the group order, 108 being 4 × 27, means elements of order 2 from D, the Klein 4 group, act weird. Their powers cycle fast, and addition modulo 2 collapses distinctions. Think, if a rep had a matrix like beginning with a 1 of 1, -1, and -1. In char 0, eigenvalues 1, -1, clear split. In char 2, that -1 becomes 1, since -1 equals 1 mod 2. So it looks like beginning with 1 of 1, 1 light of 1. And char 2, the same eigenvalues, but now it's defective, not diagonalizable. Boom, the symmetry hides, because the field can't tell different from same when 2 kills the difference. Blocks emerge as the fix. They're like force fitting. Since char 2 blurs some reps, nature bundles them together so the math still works. You don't fuse char 0 irreps directly. Instead, those 20 ordinary ones decompose via the decomposition matrix into the 11 modular ones, but only within blocks. If 2 ordinary irreps share a block, their modular pieces are linked. You can't split the kit. For your G, maybe one block has 3 modular irreps, say degrees 1, 1, 3, meaning char 2 glues
Okay, but
actions
stop for a second there. So, but still, in the problem that we just studied, like at the end of the day, you can see that from the 11 modular irreps, you still make that still doesn't match the blocks, right? So, because at the end of the day, the code that you gave me executes and it calculates that there is 5 blocks. So how do you go from the 11 modular reps to the 5 blocks?
Right, so you ran it and got 5 2 blocks, but only 11 modular irreps. That mismatch is exactly the point. The blocks group those 11. Think of it like 5 lunch tables. 11 people sit down, not 1 per table. Each block is a closed subsystem. The 11 modular irreps, the people, get assigned to one of 5 blocks based on how their underlying algebra chunks connect. Some tables have 1 person, a solo irrep. Others have 3 or 4. Those are fused, because in char 2, certain symmetries can't be split. The decomposition matrix shows it. If you look at the columns, modular irreps, they're not all in different rows of blocks. Many columns live in the same row, meaning they're in the same block. Why 5? Because the defect group, your silo 2 subscript, order 4, has a size defect 2, and the number of blocks equals the number of 2 regular classes, modulo the fusion. But GAP's nrep blocks G, 2, already did that math. For your G, the extra special 3 group action hides enough symmetry that only 5 independent bundles emerge. Bottom line, 11 irreps, 5 blocks, means the algebra isn't fully split. 5 tables, uneven seats. If it were 11 blocks, every rep would be isolated, clean. Here, nope, char 2 forced gluing.
And how do you calculate the decomposition matrix just at a high level?
Easy, high level. The decomposition matrix is just how much of each new toy fits into the old ones. You start with the ordinary character table, your 20 irreps in char 0. Then, for every ordinary irrep, QI, you ask, if I look at it only on odd-ordered elements, the 2 regular stuff, what does it look like in char 2? That gives you a function. Call it QI odd not. Now, those 11 modular irreps, the Brouwer characters, phi j, form a basis for functions on odd elements. So you solve a system. QI odd not equals sum j, m of ij, phi j, where m of ij are non-negative integers. How many copies of modular irrep j hide inside the old I? That row of m of ij is one row of the matrix. Repeat for all 20 old irreps. GAP does it by 1. Pulling the Brouwer table, the phi j. 2. Projecting each ordinary QI onto the odd classes. 3. Solving via orthodontry, since Brouwer characters are orthonormal under the sum over odd elements inner product. No guesswork, just linear algebra over integers. End of day. 20 times 11 matrix. Rows are old worlds. Columns are new pieces. Most zeros, only non-zeros within the same block. Magic? Nah, just counting.
Okay, give me a second. Be back.
Take all the time you need.
I mean, again, let me try to kind of go from the top to the bottom. So to me, it makes sense the following. So you start with basically the purest form of the group. You count conjugacy classes. This makes total sense intuitively because a conjugacy class is basically grouping the symmetries. And then these essentially, it's just in an ideal char zero world, you're getting basically the same amount of blocks. Cool. Now, when you say char 2, you're adding modularity to your arithmetic of the field, which obviously and clearly is going to hide some of the symmetries. So you're not so then this is where the first question I have across, like if I follow this reasoning. So now if I have the conjugacy classes, how do I know? Is there an intuitive way to calculate from the conjugacy classes which ones will actually merge because of the char being 2?
No, not intuitively from the list, because the merge isn't about which classes disappear, but which stop mattering. Here's the clean trick. In char 0, every conjugacy class votes. In char 2, only 2 regular classes, odd-ordered elements, like powers of your 3-group S, get a voice. The others, any element with even order, exe, stuff tangled with your Klein 4, D, goes silent. Why? Because in f of 2, adding that element twice is 0, so its action collapses. No more fine symmetry split. So to count, 1. Look at your 20 reps, e.g., F14, F2, F4, dots. 2. For each, compute order rep in gap. 3. Cross out any with even order, say 2, 4, 6, etc. 4. What's left? Say 11 classes. Boom, 11 modular ereps. The merging isn't literal. It's that those silenced classes, via centralizers or fusion in the Brouwer sense, into the ones you keep. You don't predict which odd class merges, just that all even ones drop.
Okay,
And the
so
odd
that's very specific to our case, right? Because we're saying char 2, and char 2 means 1 plus 1 is 0. So this means that the even, I don't know, whatever even is, because I don't like, so you have, so the even, but even what is even in this case? The odd ones count, yes. The odd ones, what odd ones? What are we talking about?
even means order divisible by 2.
Yeah, I know that. What I mean is, what is it that you're looking for, whether it's even or odd? Because the conjugacy class cannot be even or odd. What are you where are you checking that evenness or oddness?
You're checking the order of the element that represents each conjugacy class, not the class itself. Classes don't have parity, but the element you pick from it. Take your 20 classes, each has a rep, like F1, F22, F1, F2, F3, whatever. For each rep, ask, how many times do I apply this element until I get back to identity? That's its order. Say 1, 2, 3, 4, 6, 9, 27. If order is odd, 1, 3, 9, 27. Keep the class. It's 2 regular. If order is even, 2, 4, 6, etc. Toss it. 2 singular. Doesn't count in char 2. Why? In char 2, if G has order 2, then G plus G equals 2G, etc. That symmetry vanishes, so only odd-ordered elements, where 2 times isn't 0, preserve distinction. Your 11 surviving classes, all from odd-ordered reps. That's it. No magic, just odd-ordered element, survives, becomes a column in the Brouwer table. Even ones, hidden, fused into the odd ones via the algebra's collapse.
All right.
Simple.
Let's assume that I understand that. I think I almost understand that, but let's assume, okay, right. So you're looking at the order of the conjugacy classes, or the order of the element that represents the conjugacy class. Because you have that characteristic 2 is telling you that these plus these equals 0, so that's where the modularity happens. Fine. So now you have so this is going to give you basically, so yeah, let's say it gives you a certain amount of irreducible representations or irreducible modular representations. Now, how do you calculate the grouping in blocks from these representations?
Blocks come from how those surviving, odd-ordered classes interact under two-power fusion. High level, once you've got your 11 odd-ordered classes, they're the atoms in char 2, but they don't all float free. The algebra, ReaBef2G, is some of those atoms get glued together, not by merging classes, but by non-split extensions. One irrep can build on another without breaking apart. That gluing happens inside blocks. Think, the group has a 2-si low subgroup, D, order 4. That 2 part acts like a defect. How much symmetry leaks? Blocks are labeled by orbits of this defect under conjugation.
Stop for a second.
You don't count them from the
stop
11
for a second. What is the defect in that context?
Defect? Quick gut check. It's how big the 2-part messes up your clean math. Picture, your group G has order 108 over 4 times 27. The 2 defect of a block measures the size of the silo 2 subgroup, here D, divided by Klein 4 group, order 4, 2 times 2 cubed, that lives inside that block's algebra. Specifically, defect 0, no 2 mess. Block is just a matrix ring over the field, totally split, 1 irrep per block. Defect 1, 200 by 2, some gluing. Defect 2, 200 by 2, 4, more gluing, like your case. For each block, the defect is the exponent D, where 200 divides the order, but 200 BW doesn't. Tied to the defect group, a subgroup of D, order 4, isomorphic to C2, or C2KC2. Most blocks for G will have defect 0 or 1. Principal block often defect 2, others 0, 1. Why care? Higher defect and more hiding. In a defect 2 block, up to 3 or 4 of your 11 modular irreps can clump together. Symmetries don't split cleanly because the 2-part locks them via projectives, like adding 1 plus 1, 4, 0 forces extra glue. In defect 0, 1 irrep, no fuss. So your 5 blocks, some have defect 0, solo, some 1, pairs, maybe 1 defect 2, triple. Gaps prime blocks, ord TB to defect, lists them, run it to see. Defect is how much char 2 punches the structure.
Okay, and how do you go from the 11 modular irreps to the blocks? What are you doing? You're counting the defect? What are you doing?
You're not counting defect first. You count blocks first, then defect tags along. Step by step, super simple. 1. Take the ordinary character table, 20 irreps. 2. Look only at odd-ordered classes. That gives you the eletons, the modular irreps. 3. Ask Gap, which of these 20 old irreps live in the same 2 algebra chunk? That's what prime blocks does. It spits out a list, like 1, 1, 2, 2, 2, 2, 3, 3, 4, 4. Each number is a block label. Count the max number, say 5. 5 blocks. 4. Now, per block, list which old irreps are in it. Say block 1 has irreps 1, 2, 3. Block 2 has 4, 5, etc. 5. Cross-check the decomposition matrix. For irreps in block 1, only columns 1, 2, 4, say, show up non-zero. So block 1 owns modular irreps 1, 2, 4. That's 2 or 3 glued together, not split. Repeat for each block. 6. Defect. Gap gives it free.
Okay,
in prime blocks,
Stop.
runs.
Whoa. Okay, but that's definitely polluted. I should do that in a thread, actually. Can I do that in a thread? No, I can't thread. Oh, yeah. I should have done this in a thread. Start a thread. Oh, no, I cannot talk to a thread. Okay, it's all right. It's all good. Okay, so I think I understood the first question. So what's the effect of going from char 0 to char 2, but not too much about like how do the irreps then, the modular irreps, how do you map these things to blocks? That's there. I'm missing something there. I'm definitely missing something there. But okay, the tool, the Gap calculated it for me, but I'm missing something there. I'd like to actually understand that. Give me a second, guys, because I'm checking something else in the meantime. So I spoiled the thread now, but because now it just, and I can't navigate that so easily because the conversation just went crazy. But it's good. It's good. It's okay. So we're now okay. I'd like to understand that a bit more. The composition matrix. Explain me more. I'm trying to understand characters and how to calculate the composition matrices. Can you give me a simple example I can follow step by step? That's what I'm missing, really, I think. Guys, I might have to stop. I think baby's waking up. But I mean, I solved it, man. I solved it. 5. Come on, Grog 4 fast. Show me. I'm gonna do a summary video. I'm gonna do a summary video of my experience trying to learn and solve this with Grok. Okay. Okay, that's still thinking. I would love to fully learn that to close the gap. It just doesn't feel good that the code calculated it for me without me at least knowing a little bit, like having scratched a little bit the surface of like what is it that, you know, I understand now from chart 0 to chart 2, but I don't understand how to go from the EREPs, the modular EREPs, to the blocks, right? And this defect thing and whatnot, whatever. So that's what I'm hoping to learn with that simple example. Anyway, yes, that's good. So I'm gonna probably do a bonus video on these, and then kind of like a wrap up video. See you.